Good day, everyone. So before we begin, I would like to greet each and every one of you. Thank you for being here today. I hope you are all doing well. And now let's begin our discussion. So our topic is all about generators. So now let us first discuss what is induced EMF. So induced EMF or the electromotive force is the voltage or electricity produced when a magnetic field changes around a conductor like a coil or wire. This happens when a magnet moves near a coil or the coil moves through a magnetic field or the magnetic field itself changes. If a coil experiences a magnetic field that increases over time and the rate of the change of the field doubles, the induced EMF will also double, since EMF depends on how fast magnetic field changes. Doubling the rate means the EMF will also double. The SI unit for induced electromotive force or EMF is the volt. As you can see in the sample problem, a battery creates a potential difference of 9 volts across a circuit. What is the EMF? As you can see, the answer is 9 volts because EMF is measured in volts, just like voltage because it represents the potential difference created by a changing magnetic field. So now, what is induced EMF used for? So first, we have electric generators. Convert motion into electricity or use in power plants. Second, we have transformers. Change voltage levels for safe electricity delivery. We also have wireless charging. Transfers power without wires using magnetic fields. Induction tubes. Heats path by inducing current directly in the metal. We also have maglev trains, use induced EMF for smooth, fast, and no contact movement. And the last one, we have electric guitars and microphones. Use vibrations to create electric signals via induced EMF. Induced EMF is the reason we have lights, phones, trains, and electricity. It shows we turn motion or changing magnetic field into usable power. So now, why is induced EMF important? It's important because it is how we produce electricity in most of the world today. Without induced EMF, we wouldn't have power plants, electricity in homes, and many everyday electronics.
Hello everyone, I'm Lloyd, and in this video I'll be talking about magnetic flux. Magnetic flux help us understand how magnetic field pass through a surface. This is important because it's the reason why we can generate electricity in power plants and how transformers and electric motors work. Magnetic flux is just the amount of magnetic field that goes through a surface. Imagine sunlight shining through a window. The more sunlight that passes through, the brighter it gets. In the same way, the more magnetic field passes through a surface, the more magnetic flux there is. There are three things that affect magnetic flux. First is the magnetic field strength, or how strong the magnet is. Second is the area. A bigger area collects more magnetic field. And the third is the angle between the magnetic field and the surface. Magnetic flux is strongest when the field goes straight through the surface or when it's at a 90 degrees angle. If the surface is flat or turned sideways, less flux goes through. So this is the formula for magnetic flux. This means that magnetic field strength times area times the angle's cosine. Now, what happens if the magnetic field or area changes? Then the magnetic flux changes too. And when that happens, it can create something very useful, electricity. This brings us to something called Faraday's law. When magnetic flux changes, like when a magnet moves through a coil, an electric current is created. This is called electromotive force or EMF. The faster the flux changes, the more EMF is produced. This is how generator works. In a coil of wire, flux depends on how it's placed. If the coil faces the magnetic field directly, the flux is strong. If it's turned sideways, very little flux goes through. The unit of magnetic flux is the Weber, written as W-B. 1 Weber happens when 1 Tesla of magnetic field passes through 1 square meter of area. So to sum it up, magnetic flux is the magnetic field passing through an area. It depends on field strength, area, and angle. When magnetic flux changes, it can create electricity.
Faraday's law of electromagnetic induction is one of the most significant discoveries in the field of physics and electrical engineering. It was discovered by Michael Faraday in the 1830s, and this law revealed that an electromotive force can be induced in a conductor when it experiences a change in magnetic flux. This discovery was a major breakthrough, showing that magnetic fields and electric currents are intrinsically connected. So in Faraday's law, it states that the induced electromotive force in a closed circuit is directly proportional to the rate of change of magnetic flux linkage through the circuit. So this means that when the magnetic flux passing through a coil or a conductor loop changes over time, an EMF is generated which can drive a current if the circuit is closed. So we have here the mathematical expression of Faraday's law, wherein E represent for induced EMF, N represent for the number of turns in a coil, and the d pi over dt represents the rate of magnetic flux. To understand Faraday's law, it's essential to first understand magnetic flux, which is the measure of the magnetic field passing through a given surface. So we also have here the mathematical expression for the magnetic flux, wherein the pi represent the magnetic flux, B represent the magnetic field strength, A represent the area of the loop, and the cosine represent the angle between the magnetic field. The greater the magnetic field or the larger the loop, the more magnetic flux is captured. If this flux changes due to its motion, field strength variation, or orientation change, an EMF is induced. The magnitude of the induced EMF depends on several key factors. First, we have the number of turns. More coils means more induced EMF. Second, the rate of change of magnetic flux. Faster flux changes generate stronger EMF. Third, we have time interval. Shorter times for the same flux change result in higher EMF. And lastly, we have the area and orientation of the loop. Larger area or optimal angle increases magnetic flux and EMF. Faraday's law forms the foundation for a wide range of technologies, including the electric generator, wherein it converts mechanical energy into electrical energy using changing magnetic fields, and also it includes the transformer, wherein it transfers energy between circuits through changing flux in coil. So in summary, Faraday's law relates changing magnetic flux to induce EMF. It is also the cornerstone of the electromagnetism and electrical engineering, and it is the key to understanding how energy is converted and transferred.
This is a bar magnet and this is a pickup coil connected to a light bulb. Around the magnet, there's an invisible magnetic field. You can see the arrows here showing the field lines. Faraday's law says that when the magnetic field passing through a coil changes, it creates an electric current. That's what we are going to see now. As I move the magnet toward the coil, watch the light bulb. It lights up. Why? Because the magnetic field inside the coil is increasing and the change creates a current. Now, I'm moving the magnet away. The light bulb lights up again, but the current flows in the opposite direction. That's because the magnetic field is decreasing. If I just hold the magnet still, the light bulb turns off. Even though the magnet is strong, there's no change in the magnetic field, so no current is made. Now, if I move the magnet faster, the bulb lights up brighter That's because a faster change in the magnetic field causes a stronger current. If I flip the magnet and move it, the light bulb still lights up, but the current now flows the other way because the magnetic field direction is reversed. In short, by moving the magnet, we are changing the magnetic field inside the coil. Faraday's law tells us a changing magnetic field creates an electric current. That's why the light bulb lights up only when the magnet is moving.
Let's talk about the Lenz's law. Lenz's law is the nature's resistance to change. Imagine you pushing a heavy box across the floor. It takes effort, right? Lenz's law is like that for magnetism. It's nature's way of resisting changes in magnetic fields. Whenever a magnetic field changes near a conductor, like a wire, the conductor generates a current that tries to counteract that change. Think of it like this: the box, pushing, and the resistance. When it comes to the box, the magnetic field is like the box. When it's pushing, changing the magnetic field is like pushing the box. And the resistance, the conductor's induced current, is like the box resistance to your push. Now let's move on to the Lenz's law formula. Lenz's law is part of Faraday's law of induction, which is expressed as electromotive force or EMF. The induced voltage or electromotive force in the conductor. Negative N is the number of loops in the coil, and the change is the magnetic flux or how much the magnetic field is changing, and the change in time. The negative sign tells us that the induced current will flow in a direction that opposes the change in magnetic flux. And let's talk about the Lenz's law experiments. In his first experiment, it is increasing current in a coil. Imagine a coil connected to a battery. When you turn on the battery, the current starts flowing, creating a magnetic field around the coil. As the current increases, the magnetic field gets stronger. Lenz's law says the coil will try to resist this change. It does this by generating an opposing magnetic field, which is created by an induced current flowing in the opposite direction. In his second experiment, it is moving a magnet towards a coil. Imagine a magnet towards a coil of wire. As the magnet gets closer, the magnetic field strength through the coil increases. Lenz's law tells us the coil will try to oppose this change by creating a magnetic field that pushes the magnet away. In his third experiment, it is pulling a coil away from a magnet. Now imagine again pulling a coil away from a magnet. As the coil moves away, the magnetic field strength through the coil decreases. Lenz's law says the coil will try to resist this change by creating a magnetic field that pulls the coil back towards the magnet.
The motional EMF is the potential difference created across the ends of a conductor when it moves through a magnetic field. The motional electromotive force, or the EMF, is a fundamental concept in electromagnetism that describes the voltage generated across a conductor when it moves through a magnetic field. This phenomenon is a direct consequence of the interaction between the magnetic field and the moving charges within the conductor. Understanding motional EMF is crucial for various applications, from electric generators to understanding the behavior of charged particles in magnetic fields. So how does it work? So when a conductor moves through a magnetic field, the free electrons within the conductor experience a magnetic force due to their motion. This magnetic force causes the electrons to drift towards one end of the conductor, creating a potential difference or voltage between the ends. So at the heart of the motional EMF lies the Lorentz force. This force acts on a charged particle moving in a magnetic field. The magnitude and direction of the Lorentz force are determined by the charge of the particle, its velocity, the strength of the magnetic field, and the angle between the velocity vector and the magnetic field vector. Specifically, the force is proportional to the charge, velocity, and the sign of the angle between the velocity and magnetic field. When a conductor moves through a magnetic field, the free electrons within the conductor, which is the charge carriers, are subjects to the Lorentz force. Since the electrons are negatively charged, the force acts in a direction perpendicular to both their velocity and the magnetic field. This force causes the electrons to accumulate at one end of the conductor, leaving a deficiency of electrons, or positive charge, at the other end. This separation of charges creates a potential difference, or what we call the voltage, across the conductor, and this potential difference is what we call the motional EMF.
Good day everyone. So now we are down to our last topic. So today I'll be going to talk about generators. So generators are the machine that help turn mechanical energy into electrical energy. So let's keep it simple. So generators work based on Faraday's law of electromagnetic induction. This means that when a coil of wire spins in a magnetic field, electricity is produced. The faster the coil spins, or the stronger the magnetic field, the more electricity we get. So we have two types of generators. We have the AC generators, which gives us alternating current. When the coil spins in a magnetic field, it uses slip rings and brushes to move the current to the outside circuit. The current changes direction, that's why it's called alternating. We use this in our power plants, homes, and cars. And the second type is the DC generator. This gives us direct current. DC generators look similar with AC generators, but it uses a communicator instead of slip rings. The communicator flips the connections to keep the current flowing in one direction. We see DC generators in batteries, chargers, and small motors. So now let's look at the main parts of a generator. So first we have armature. This is the coil that spins and creates electricity. Next we have magnetic field, provided by magnets and electromagnets. Next is we have rotor, the spinning part which holds the coil. Next we have stator, the stationary part that holds the magnetic field or coil. Next is we have slip rings. In AC generators, these connect the coil to the outside. While on the other hand, we have communicator in DC generators. This makes the current flow in one direction. Lastly, we have the brushes. This transfers the current from the rotating parts of the circuit. And now, here's how generator works step by step. First, something spins the coil, maybe wind, water, or an engine. Step 2, as the coil spins, the magnetic field through it changes. Step 3, this change creates voltage, we call it EMF. Step 4, if the coil is connected to a circuit, the EMF causes the current to flow. Lastly, step 5, in an AC generator, the current changes direction, while in DC generator, the current flows in one direction. So to wrap it up, generators are all around us. They use a spinning coil and a magnetic field to produce electricity, and depending on how they're built, with slip rings or with communicator, we get either AC or DC electricity. Thanks for listening. I hope this helped you understand how generators work in the simplest way.